talking to us as we walk in,
Yeah, and it just turns into a conversation, and we just roll right into class, and I don't really think about it.
because no one in those classes talks to them.
No one in those classes talks to. I actually, it's funny to like see how it progresses over the semester. Like at first, it's like crickets. Like you can ask questions and nothing. Now it's people are asking questions. They feel more comfortable. Right? There's pockets of people.
They don't understand it.
Yeah, then I'm like, shit. Did they have all these questions like way back? Probably,
Probably.
based
They
on the
just
grades.
didn't wanna ask the question,
Yep.
but they didn't realize they didn't get it.
Yep.
That's what happens.
Okay, so those were the forces, right? We used our shape functions. We used our shape functions to figure out our energy equivalent body forces, which came from our self weight, and then our tractions, okay? Which, as we discussed on Monday, they could come from a wide range of sources. So what is this idea of condensation? Why do we want to know about it? Well, a lot of software programs have quadrilateral elements, okay? And those quadrilateral elements, they actually establish a fifth node inside the element, and they establish 4 triangles, okay? This is what VA does, right? So in VA, when we start drawing plates, okay, you can draw a little plate tool, you click 4 times, come around the corner, okay, and you can get a 4-noded plate element. Or you can figure out, or you could establish a 3-noded plate element. VA allows you to do either one. Okay. How do we establish that? Well, they throw this node in there. The computer makes it. Guess I could zoom in a little more. Man, it's so nice outside. Should have.
You don't have, well, you still can park behind the labs, but you can also just park.
Whoop, CTS, CST, a little dyslexic there. I always park behind the labs. It's my parking spot. Behind the labs. It's a tiny bike, it fit, like, it
That's
doesn't
what I'm
take
saying.
space. Yeah,
Yeah, I parked there a bunch of the summer.
Don't you have to get a permit to park in the other places,
You
technically?
only need like the $100 one, which is.
To park in like the boulevard over here, like in the parking lots for motorcycle parking?
You still
Wow,
one stop where you just
$100.
get to like F the stadium lot one,
Yeah.
and that's the same. It, like,
Oh, then you can do all the
so I do
motorcycle?
Stadium and the motorcycle.
Sick. I'm cheap and I go park on Wilson if I don't park behind. You park on Wilson too.
I see that.
Yeah.
Shitty truck gang.
Yeah. Hey, I don't know about your truck. My truck is not shitty, okay? I love my truck.
That's right.
I love my truck.
Me too.
Don't you?
I love my truck.
Yeah, I wouldn't
Everyone's
call it
your
shitty. It's like
second
beautiful,
truck,
dude.
Because your other shitty truck doesn't work.
Yeah.
Especially gas prices are like whatever they are now, $4, right? Over $4. That's crazy.
What did you try last summer?
Like 25-ish, 24-ish.
Can it make it?
2-wheel drive. It's got a huge gas tank. It's like 24-gallon tank, so I can go 400 miles.
Can the truck make it 400 miles consecutive?
Oh yeah.
That's what I worry about with his truck.
Really? I drove it to Great Falls last week and back. Crushed it. Has AC. Mine's a lot better shape than Aaliyah's. That's why it's like shitty truck gang. It's like, yeah, you might be a dumb gang. I'm not. Okay. Did you get like the clunking and the weird stuff fixed?
Yeah, actually, there's some of it has been fixed.
Okay.
Just still-
Okay, good. All right, so what happens when we add this fifth node? Well, we have 4 elements now, right? We're gonna have 4 CST elements, and we would then assemble them into a structure matrix that makes up this one quadrilateral. Yes, Aaron?
So do we have compatibility along all edges of our 4 elements, or just at nodes?
You would, right?
Because of the shape. is the
Because
same.
of the element that you use to create that shape, right? Because we're saying, in this case, right, if we did condensation of this quadrilateral and we used 4 CST elements,
Okay.
based on the fact that we're using the constant strain triangle as our element, that element's shape functions are such that if we are looking for the displacement between, say, node 5 and node 1 of element 1, right, they're only a function of node 1 and node 5.
So it'd be the same as element 2.
Same element 2, 3, and then it would be the same. we're gonna talk about compatibility, equilibrium and stuff, right? That is associated with displacement. It gets different when you get to stresses, right? Because stresses then start incorporating all of the elements and you lose that, what we call equilibrium, right? The forces that are acting along that line are not equal from one element to the other. But yeah, good question. You could pick an element that didn't have compatibility, and that would be a bad element because that would hurt you with respect to convergence and things like that, right? You're gonna end up getting steps of weird shit happening between all the elements. You don't want that because that doesn't really capture what's happening in the real world either, right? So yeah, so you have this quadrilateral. You say, screw it, I don't want to do a quadrilateral. I'm going to add a fifth node. They add a fifth node. They create 4 triangles. Those 4 triangles they can assemble into an assembly, right? A structure matrix that associates the equilateral triangle into 4 CST or 4 triangular elements, okay? True condensation, okay? We're going to deviate a little bit from what VA does, but true condensation, all right? No loads are allowed on node 5. What does that mean? That means Fx5 equals y5, and that equals 0. And whenever we have nodes with which we govern it not to have forces, right? That's the same as when we have a released beam, right? We're saying that we're going to release rotation, okay? We're going to release fixity. It's going to be able to travel, right, in one direction. It might not be able to rotate. We talked about how that works. Well, in order to do that, if you remember, we take this now assembled matrix C and we start partitioning it, right, rearranging it based on the fixed degrees of freedom and the released degrees of freedom. So we end up with this, if you remember, KFF, right? KFR. This is KRR. And this is KRF, right? Where we have our rows with respect to fixed degrees of freedom, right? Fixed just being that it can transfer forces, right? We can have forces in these degrees of freedom. We have the columns associated with the fixed degrees of freedom. The columns associated with the released, and the rows associated with the released. When we partition this and we rearrange our stiffness matrix to incorporate these fixed and released degrees of freedom, we also rearrange our displacements, right, in the fixed and displacements in the released, right? And again, all back to our fundamental equation, right? We have force equals stiffness times displacement, right? F equals KD. So in our, this is all has to equal our reactions or our forces, right? We would have fixed reactions and forces for degrees of freedom with which we have fixed, where we didn't release the forces, right? Where we can transfer forces. And then when we don't, we're gonna say everything that we release, it can't transfer force, right? So those have to be 0.
So what's the benefit of doing this condensed quadrilateral instead of just having 3 CSTs that all go together and you can put a force at the fifth node?
It has,
Measured node.
yeah. It has to do with simplifying, well, allowing you to use a triangular element and the displacement function that comes with assuming, say, a CST versus a quadrilateral. And the CST has convergent characteristics that are better than, say, some of the quadrilateral elements. Okay. Also in a software program, it allows you to do both, right? Now in a software program, you can then model a plate with 3 noded elements, or you can model it with 4 noded elements, right? Me as the user, and it's going to convert it for you automatically. It also helps, like VA does, which is not an educational version, but it does auto meshing. And so you can actually create, Adam talked about areas, right? These elements, well, they're not even elements, right? They're pseudo elements that provide you a means of distributing load, and they don't actually have any stiffness. Well, in the real versions of VA, I don't think in the educational, you can draw areas like you would a plate, and then you would auto mesh it. And then it would go through and it auto meshes it associated with discontinuities. It takes into account where loading is. and it'll say refine the mesh more where there's discontinuities, and then kind of make it coarser out in the field where there's not as much going on.
I guess like we've talked about constant strain triangles, and I've always assumed like we've talked about one, assuming that we could overlay and add
Yep.
as many onto it as possible, and then now we're focusing on just 4 together, and we're saying you can't put a load in the middle of the, if you have 4 together, or is this a whole different?
This is just this is a method with which you would take a quadrilateral and establish 4 triangular elements.
For somebody to just be like 1, 2, 3, 4.
Yep,
nodes,
someone could
and
just
then
draw
like-
4, and then it goes through, and in the background, it creates 3 triangles.
Right.
Because then what you could do is, you could have a 4-noded element, and then attached to it, you could have a triangular element,
Yeah.
okay? Gives you more flexibility from like a software
This is from the
standpoint.
software. so
Yes.
yeah.
Yep. And VA does this, okay, but they do it a little bit differently, and we'll talk about it in just a second. So we establish this partition matrix. We do this so that, if you remember, we come up with this new condensed stiffness matrix. See if I can get this right. So K FF minus K FR K RR K RF equals what we call this K sub E, right? Condensed stiffness matrix for the 4-noded quad. So we get one stiffness matrix that gives us the behavior for this 4-noded element that someone would draw. Assuming we don't have any loads, right? We released the ability for node 5 to have any loads. It's truly going on in the background, okay? We're saying that you can't have any forces on it. All the forces we're going to associate are these 4 nodes.
So the reason it doesn't have any force is because it's just for continuity, it's just.
Yes, it's just to
It's a
establish,
free
it's just
node.
it's a way of creating triangular elements from a 4-noded element. So you could use a CST, right?
Yeah.
Instead of using a quadrilateral element.
But does VA use like almond triangles though? Like
Yeah,
you
so
said,
then-
like
so
you said,
then-
these CSTs?
Yeah, true. But they're triangles.
Right.
And we're gonna talk about that in a second. Hey, you just keep being ahead of me. This is perfect, just pushing us forward. Man, you get a reference letter. Just ask me for one. Okay?
Yeah, dude, Aaron and I both have jobs. So.
Damn it! I thought you were still looking.
No, I
You
accept-
finally accepted?
I accept.
Nice, congrats.
I'm gonna slither in.
Where are you going?
Jersa Hedrick.
Does that not sound like the?
Yeah, it
parcel
sounds
tongue?
terrible, yeah. You're gonna have to like grease your hair back, dude. Shave your face.
They're very nice people.
Yeah, yeah.
Not like just mouth.
Yeah. Until they bring you in to do the ritual and stuff. All right, so what's important about this? As I mentioned, it allows you to use triangular elements from a quadrilateral element, okay? Allows some additional flexibility of a software package. You can start drawing quadrilateral elements instead of triangular elements everywhere, right? Knowing that they're gonna derive or develop these triangular elements. Well, VA kind of does this, as I mentioned. And I say kinda. Because they actually generate loads. Right? I was talking to Adam about this. And so what does VA do? Well, they generate that 5th node. It ends up being at the centroid of that quadrilateral, right? So that node 5 gets developed. Okay. They then, if you had body forces, right, self-weight, if you had surface tractions, if you decided to apply some sort of load in plane, or even in VA, you can do out-of-plane forces, right? We'll talk about thick plates. Okay. When you do that, it takes the energy equivalent loads based on establishing this 5th node in there, right? And it'll apply the loads to that node. And it provides you with the results for that node also. right? And so VA is using this in the background. Okay? And yes, they don't use the CST element. They end up using the Ullmann triangle. All right, so that's condensation. This ability to take a quadrilateral element and devise a way of establishing it based on triangular elements, okay? Which gives you more flexibility, right? You're not limited by the degrees of freedom and the displacement functions based on a quadrilateral element. Now you can use those functions that were based on CST elements, okay? All right, what's the next thing? This guy here, right? I don't know that I don't think there's anything for you guys to fill in here, honestly. We're running out of time, so we just gotta go. So I think I just gave you guys, the rest of these notes are just filled in. Okay? It's really easy to check out like Brandon. All right, we have visual analysis. They use elasticity elements. What are elasticity elements, right? Plates, okay? CST is good, right? It's a good performing element, but we can do better, right? What's one thing that the CST element does that might not be really associated with the real world? Results you get, right? Right, no rotations, but also, right, CST, constant strain triangle. Over that triangle, you have constant strain, which means you have constant stress. Does that happen in the real world? No, right? You can get very close to the real world if you refine your mesh appropriately, right? If you made it very, very small, you make all these elements super, super small. Now you're going to get that variation, but in reality, again, you're not going to have constant strain, right? So we can do better. We really want a quadratic displacement function would be the best. So then they came up with the linear strain triangle, right? The LST. Well, in order to, as we know, when we use our generalized degrees of freedom, and we relate that back to our assumed displacement functions, right? We would need more nodes, more degrees of freedom in order to get this linear strain, right? If we have linear strain, the strain's the derivative of displacement, we'd have to have a quadratic, right? We have to have something to the second degree. And so in order to do that, and we also, as we know, and we're going to talk about convergence, but we also know that we want a complete polynomial. We want to, if we're jumping from linear, right, to second order terms, we want to grab all the contributions, right? So that would be grabbing x times y and x squared and y squared, right? If we lose one of those, we're losing a contribution, right? We also know that we want to use lower order terms first, right? Those are larger contributions, right? They're going to be scaled differently, right? And x to the third wouldn't give you as much contribution as, say, x, right? But linear. You want to grab some of these lower order terms first. Okay? Or it might skew it one direction or another, right? If you had x to the third, right, and your x term, say, was 12, that one term, right, times that one A5 or A6 or whatever that generalized degree of freedom, it can skew the results, right? So you want a complete polynomial, you want lower order terms, and you want to grab all of them if you can. So when they devise the linear strain triangle, in order to get, right, go from these three, which is our linear strain triangle, to this, our constant strain triangle, to this whole thing, which is our linear strain triangle, we need to add 3 more degrees of freedom, right? So we need to add 3 more nodes. So they end up doing this. Okay. So it results in a linear strain or stress, and you get better results, right? But those better results come at a cost. Right? Now you've got 12 degrees of freedom. 12 degrees of freedom. So instead of a 6 by 6 stiffness matrix, now you have a 12 by 12 stiffness matrix, okay, for every single element. And so then you think you have thousands of these elements. So now you've got way, way, way more degrees of freedom, way, way, way more computational requirements. And so, yeah, you get better performance, but it's going to take you a lot longer to actually run it, right? So that's a bummer. Okay? So you get better results at the cost of far greater unknowns, right? Nodes. So this is when DJ Ullmann steps in, okay? And you guys should have gotten this whole paper, this beautiful paper. I'm sure you guys read it, right? Yeah? Did anybody even look at it? Be honest. Nobody looked at it. Sweet. Mike, you looked at it. Nice. See? Look at that. Look at all these references I'm giving today. Huh? You don't have oh, you have a job at Bridger, damn it. None of you guys really need me, I guess. All right, what did Ullman do? Well, now he took the constant strain triangle, and we all know, right, based on the linear strain triangle, that having the ability to have linear strain or a change in our stress across the element is a benefit, right? It better matches the reality. It also better helps us get closer to the exact solution faster. So it helps with convergence. Okay, so we wanted that. So what did he do? Well, his infinite wisdom back in, what year is this? 1984, before all of us were born. I think I can confidently say that, right? No one? Right? No one. Okay, good. 84. Am I the oldest in this room? Mike, am I the oldest?
I'm close, yeah.
I'm the oldest. Daniel, how old are you?
85, only
85. You were close to this.
85. I'm 67 now.
Oh yeah, you got me,
Last
man.
week.
You got me. Last week?
Mhm.
Happy birthday.
Yeah.
35. Woo!
When are you?
I'm 88.
Oh.
Thir-
My first born is 9
You're-
now.
What's that?
My first born is 9.
Wow. Damn.
My second born is 4.
Kids.
That's me.
Congrats. Congrats. I don't think I'm ever going down that road. Actually, I know I'm never going down that road. We've decided, so that's good. I'm happy for you. What do you mean? I'm older or younger than you?
You're younger, but.
So you're an 87 then. You're an 88.
She doesn't
It's
wanna
really
say-
not that hard, and you're not old enough to really like care about how old you are. 88 or 87? 88.
I'm not gonna say.
All right, May 88. May 88 is when I was born. My birthday's coming up. Okay, we won't be in class during it, but I'll take gifts
So
still.
that's what our finals gonna be.
Guessing my birthday or what?
No. That
Celebrate my
party.
birthday?
Yeah.
I did think it might be. Do you guys still do grad student like get-togethers?
We did it the end
All
of
the
last
time.
semester.
Aaron said no. You don't want to do that?
Aaron's too cool, he has friends.
Oh yeah, it's against the bylaws, dude.
I only go over to Mike's house. That's.
Oh, you don't want to come to my house?
I'll go to your house.
Oh no, sweet.
I'll go to your house.
I thought
We don't-
about
We
doing
just don't
it.
do that many grad things.
Okay, well maybe we
I don't
can
get
maybe we
invited.
could
I'm
have
just
a.
trying to organize a structures grad event. I told her I'd push for it heavily.
You haven't.
Who was doing this?
Flynn.
Oh yeah, that's true.
Well,
She
she
did
hasn't
ask me.
done it. She said when I do.
Actually, for you two, because Flynn asked me to do it, and I want to delegate to you guys. Talk to Sam Fox about. It'd be cool if we could tour the new health center. You guys worked on that at all? I think that's her project, right?
DCI did that.
What's that? DCI did that, yeah.
It's a sick building.
Right?
Yeah.
Well, what's left of it. I don't know what you guys are doing to it after that. Okay. My old boss did the
Is it
addition.
one? Which one?
Jim,
The
where's
wellness
the
center?
first?
Yes, that's why. That's my crew, right? That's my
Okay.
gang.
Not the new Billings Clinic out in Bell. That's what I'm thinking.
No, I'm talking about the health, like the fitness center here on the
The
campus.
wellness.
The wellness center. Is that what it's called?
The one they're doing right now.
The one they're doing right now, they tore like most of it down.
Yeah.
Yeah. But Flynn wanted to maybe do something where we would go walk through that and then keep walking to say Bridger Brewing or something.
Yeah, that's.
Yeah. And so she's like, can you reach out to Sam Fox? I said, yeah, I sure can, and I just haven't. So if I don't, maybe you guys can start that conversation a little bit. Tell Sam to call me.
I'll tell Sam to call you.
Tell Sam to call me. It's very important. More important than her work. Okay? All right. Let's back to Ullman. So what did Ullman do? Well, he said, all right, we're going to have translation on our nodes, our 3 nodes, but we're also going to add rotation. Right? We're going to add rotation out of, like, in the axis of the out of plane direction, right? So it's still in plane. So this is still membrane stuff. We're not talking about out of plane sort of bending. Okay? This is a membrane element. We're all talking about in plane stresses. The forces that we apply also have to be in plane, right? So we body forces, they have to be in the X direction or the Y direction. And then the rotations that we get. Well, this guy is definitely way smarter than I am, okay? Maybe not smarter than you guys. But what did he decide to do? Well, he added those rotations. And when he added those rotations, he then started devising, right, using generalized degrees of freedom, right? We see all these A1, 2, 3, 4, 5. Well, there's actually more than that, right? There's 9 of them. right? Well, actually, there's 6 of them because we can get rotations from displacements like we did in our beam element, right? And so if you read this, basically this thing is 5 coefficients and 6 connectors. Basically, you have 6 degrees of freedom along one line. You have, say, node 1 to node 2. You have 6, what they call connectors would be degrees of freedom, right? So you have translation and rotation, okay? And this problem, he says, is mathematically overdetermined and the following strategy is therefore adopted, right? So we have 4 boundary conditions and they go through and he devises, right, the stiffness matrix going through, as you can tell, we go through and he does the whole stationary potential energy. Look at that. We've got an omega. We do some weird stuff with coordinates. He talks about zero energy modes, which is kind of a downside of this element, but you can get away from it. Okay, you figure out a constitutive relationship. They call it the D matrix, his elasticity matrix. Right? Looks very similar to our plane stress case, right? Plane stress in an isotropic material, right? Does our strain energy, goes through that whole thing, right? It's pretty cool, right? You guys could read this and kind of understand it, kind of. Right? You guys can understand it. Right? It might take a few times reading it, right? We have our strain displacement matrix. Look at that, right? These are scholarly papers. Don't you guys feel educated now? You can just read this shit, okay? You guys are part of an elite group, okay? And then he goes through and he does some examples. What's the importance about these examples? Well, he basically says, let's see, which one is it here? This one right here, right? He goes through, and obviously the whole idea behind developing this triangle was in an effort to get better results, right? And better results means, 1, we can get to the exact solution. Okay, we'll talk about the patch test in a little bit, a way to test some of that. Okay, and then on top of that, we want to get there fast, right? And we want to get there as fast as we can with as minimal effort as possible, right? Because every node that we add is more computation that our computer program has to do, right? When you're in RAM, you're in RESA, you're in visual analysis, right? Every node you add slows down your results, right? How long it takes you to get results. And that's just the finite element side of things, right? That's just to compute the nodal displacements, right? Nodal rotations, your degrees of freedom for your elements. And then on top of that, Adam went through it, right? There's another tab in visual analysis, same with RESA and RAM, right? Where you actually start designing those elements. Well, now that the computer program takes the results you have and it goes through and it says, okay, do you want to design it based on LRFD for AISC 360, right? Do you want to use the Steele manual? So then it goes through all the chapters and does all the checks based on all the stresses that it calculates, right? So adding nodes can really start compounding and piling up, right? The ability to actually analyze and get results out of a program. So we want to get there as fast as we can with as minimal nodes, right? As minimal effort as possible. Okay? As fast as computers are right now, it's not that hard. Okay? I'm gonna we've been trying to track down like our Miller dining hall model, okay, to see like it doesn't take long. Like you start doing a full-size building, right, and pretty soon you have hundreds of elements and thousands of plates, right, and that starts piling on, and it takes minutes or hours. The engineering building, we had to split the whole model, and we could no longer look at it as gravity and lateral. We had to separate them into 2 models. We had a model that's all it was doing was gravity loads. The other model was all it was doing was lateral loads, right? Because it just took so long to compute. And so in this case, right, when we started getting to, he looked at 3 different mesh sizes. The LST element you can see, right? These are the displacements that it's getting, tip deflection, the cantilever beam under a point load. Okay, you can see that this new element got pretty close to it, right? Versus this CST element. Right? Look at that first mesh size, very, very coarse. Big difference, right? Big difference. Okay? And so it is a huge increase in efficiency of this element, and so then that's why VA uses it, right? So it has a node in VA, displacements in plane, and rotations in plane, and that's why it uses the Alden triangle. Okay? What else does it use? Right.
That still makes gives you a 12 by 12, right? Even though you're not adding a node, you're adding a degree of freedom, right? So it's
Because-
still,
No, because the way that it's doing it is, just like in our variational beam element, right? When we calculated rotations, those rotations are a function of displacements, right? Slopes, second derivative displacement sort of thing, right? And so you can relate that third degree of freedom back to the original displacement. And so you can, then it allows you to take those generalized degrees of freedom, the extra ones you have, right? There's 9 of them for this whole triangle, and you can use them between our translations, and then that's what his derivation does, is it creates this relationship between, what he does is he says, okay, we have a transverse displacement along an edge, if we were looking along the edge. He orients his coordinates with respect to a transverse displacement and a parallel displacement, right? How far does this node displace along the side, and how far does this node displace perpendicular to the side? And then he relates that back to rotations.
So 9 by 9 or 6 by 6?
It would be it'd be a 9 by 9 because you have 3 degrees of freedom at each of the 3 nodes. So less, right? Yes.
Oh, you-
Nope. This is your world. Come on.
I'm just getting a little confused, like in visual analysis, when you like put a node and then you like connect those nodes with a bar element.
Yep.
Or you make a square of bar elements, and then you like put a shell inside that square. Do you just have like a
And see, you make a square with bar elements. Is that what you're saying?
You wouldn't do that. They're two.
It depends on what you're modeling.
Well, like I was imagining that example that he gave where they just weren't connected at all. Like he had the members and
Yep.
then he had like the areas or the shell or something
Yep.
on top of those.
He had a
Or a plate.
plate.
Oh, plate, not shell.
Yes, hit a plate. Yes.
And I guess I'm just getting confused how you know like when to use which one and then how you know that everything's connected how it's supposed to be connected.
That comes with experience, I would say. But on top of that, a good understanding of what's going on in the background, right? So the finite elements only know what's happening at nodes. So what was happening in that example is they would take all these rafters, right? Everyone kind of saw it, right? We had a house. For those of you that decided not to be here, okay? So it had a bunch of rafters on it, right? Had a big ridge beam sitting here, and raftered a wall, right? And what people did, okay, the designers were doing, is they had all these rafters. They were dimensional lumber. I think they were 2x6s, right? So they had a bunch of 2x6 rafters, okay? They had a bunch of wall members, and then what they did is they said, okay, right? We had, say, one rafter that was sitting on the end, right? Some gable rafter here, and a gable rafter here, okay? And these rafters, right? Everything has nodes on it, right? So we have these nodes, right? The ends of the end rafters, okay, have a node on each end, okay? And each one of these had nodes, right? Boom, boom, boom in here. And then we got different colors, sweet. Then what they did is they said, okay, well, we have sheathing on our roof, right? Makes sense. We would add this plate element over the top, one big plate, right? So if we add a plate, one single plate element, right? What's VA do? It says, okay, we got a node right there. We've got a node right here. We've got a node right here. Got a node right here. And it does this, right? Adds this 5th node. We don't see that in the user interface, right? But that's what it does in the background. So we have these 5 nodes. Looking at that, do you see a problem?
Because it's not connected at all those.
It has no idea.
Okay.
And so what's happening is, right, and then you had, what they had was, they had these plates, right? They had a plate here and a plate here,
Which also is.
which isn't connected to these rafters,
you
right?
wanna mesh it to be
You would have to, yes.
on each of those net, like.
Yep.
Well,
Like-
the other they modeled it. Didn't he say the other way was to do like an area?
How many questions you guys got here, right? What, James?
They said like an area might be better, or there's like the way to like automatically.
Yeah, so-
distribute it.
So the way, what they were doing is my guess is what they were doing is they wanted, say, I have snow load, and I don't want to go through and apply that snow load to each one of these rafters. Yeah,
Okay.
that's what I said. Okay, so what do? They draw a big plate in here, and then I say, okay, the plate allows us to do an out-of-plane pressure. Okay, we've been looking at in-plane, like CST is in-plane forces, right? Well, they use what's called thick thin plate, which was derived, and we're gonna go through that in a second. But that allows us to do out of plane stuff, right? So it allows us in VA, you click on the plate, you say apply a plate load, right? You could apply a pressure, all this linear distributed pressure, all that stuff. So you would apply the snow load, maybe you'd apply the dead load, maybe you'd apply a roof live load, something like that, right? And then that would be applied on this plate. Well, that has no, it has no way to get to these rafters. It has no idea that these rafters exist. The only thing it knows exists are these 4 nodes, right?
So that's why the 2x6s were good.
That's why the 2x6s were good, which also scares the shit out of me, right?
That makes sense. I
It's
guess.
just like, we've been designing this forever, and and now we're getting it over steeled, right? Is the comment that they made in the email.
That makes more sense. Thank you.
But you can see in their mindset, I mean, in general, that's what they were trying to do, but without understanding what's going on in the background, the VA does not do that, right? So what does VA do? Well, they say, okay, we understand that there's a benefit to having a method of being able to apply loads. So they came up with an area. So you can draw an area, okay? You draw it similar you would draw a plate, okay? But it has no stiffness, okay? It's not devising a stiffness matrix. All that an area does is gives you a means of transferring loads, okay? When you draw an area, look at all these colors, this is beautiful. When you draw an area, it'll show up and it'll have span directions show up, right? So what is that doing? Well, that's saying, okay, every load that I put on this area, I'm going to span it over whatever members are intersecting that area. And so it is a beautiful tool if you wanted to, say, do a big floor system, right? And in a general office building, like NAH for instance, there's laboratories, right? You might have 125 pounds per square foot for live load. Second floor corridors and above, 80 pounds per square foot, right? The basement, there's a ground floor level, 100 pounds per square foot for exit ways, all that stuff. Classrooms, 50, you go through the whole book. So you're devising this thing, all of a sudden you got all these little areas everywhere. And it allows you to quickly iterate between sizes, right? And not have to worry about the fact of, okay, if I do it a plate, how does that plate affect the stiffness too, right? Because now you're putting a plate in here. One thing we haven't talked about, we'll talk about when we start modeling, is the fact that everything you model in VA is centerline, right? Okay, if you go to the picture view in VA or RAM or RISA, they're doing, right? They're gonna show you this nice, beautiful, wide flange beam, right? Well, a lot of times we might have something like this, right? Where we have concrete sitting on top of a metal deck that's sitting on top of this beam. This beam might end up having a composite beam. You have these headed anchor studs sitting in there, right? Spaced at 12 inches on center or something, right? This is gonna add stiffness to this beam, right? Well, if you draw a plate, if you're like, hey, I want to add that stiffness, I'm going to draw a plate. This is where VA draws a plate, right? Doesn't give you quite the stiffness that you thought it would, right? Okay, there's things in VA where you can offset this up above, okay? You can ignore it altogether, right? There's ways you can work through it. Okay? So again, you got to, experience is a big part of it, right? Because now that I've been through this problem, I know that when I draw this, if I'm really trying to depict this stiffness, I need to really think about the fact that VA is doing everything centerline to centerline, right? Okay. But I figured this out based on the fact that I know what's going on in that the finite element method only looks at nodes. Okay. Yes, sorry.
In VA, what do the orange bubble nodes mean?
Released.
You know what I'm talking about?
Orange bubble nodes. Oh, where members intersect?
Yeah, I think it happens if you draw 3 nodes and draw a beam all the way through it. Is
Yep,
it,
cross it, right? Like if you had a brace frame, say on this building we had a brace
Yeah.
frame that does this, right? And then right here it does that.
Yeah.
Well, in VA, gives you the option, right, is whether or not those are connected, right? Should VA treat that as 2 members, right? This would be member 2 and this is member 1, right? This is member 3 and this is member 4.
Yeah.
Or should we just have 2 members here, 1 and 2?
What's the default, I guess?
I do not remember. If you click, you either have to click on the member or you have to click on the node. I think it's the member, and it'll say connect at intersection. And then I think it'll generate the node.
I know what you mean. But it's not, if it's a bubble node, it doesn't register as the
I don't know, I guess it's been a while, I would have to go back and look at the depiction.
It's
and then-
sometimes I'll do that kind of like with the rafters where it's like you put in all the nodes and you draw like the big ridge beam, and
Yep.
then you can connect the rafters to that beam with those nodes? Does that make
Oh,
sense?
so
Like
if they, yeah, so like, you essentially draw the rafters in, and then you draw this ridge beam in, and then all of these become one of these.
Yes.
Yes.
Does that
You would want
transfer
to,
load?
you either have to click on the ridge beam or the rafter, and in those, you would say connect at intersections. Like on there, it'll give you a little option to say connect at intersections or not. If you say that it connects at intersections, then VA goes through and he automatically divides a node there. And it says, okay, we want to connect to this beam. Okay. The other, yes, and that's what you would want, right? Because there is a physical connection between this rafter and this ridge beam.
Okay.
And if you didn't do that, then it would not know that that's there.
Okay, that's what I was wondering.
Well, you could go through and you click on the ridge beam, you say, do not connect at intersections, right? And then it should be, your deflected shape, you could look at your deflected shape and say, does that make sense? Well, it wouldn't, because if you had dead loads and live loads on all this shit, right, and this thing starts deflecting, this node will no longer be sitting at the center line of that ridge beam, potentially. Right? Can you also imagine, like, if they offered a place in Shell's class, okay, 'cause I have used this in the real world.
Yeah, I do.
Okay, you should take it.
It's just not in their window of, you know what I mean? You only get
Some
2
of you.
years, yeah.
Who's graduating this semester?
Even
Who's
in
trying to
2 years,
graduate this semester?
There's enough classes you can take that you don't need to like.
You don't have to take it?
There's a lot
It's
of
really
just
cool though.
civil ones.
What it really highlights is the crazy amount of stiffness you get by having in-plane membrane action, right? When you have like the roof of the field house, okay, the sheathing on the field house provides a massive amount of stiffness
What's
for
so
the
special?
roof. What's that?
Is it like a 2 layers of sheathing, or I don't
No,
know?
it's just the way in which it is acting, right? So that at the center of that dome is like an oculus. It's a big metal ring, and all of these glulam beams go to it, right?
Okay.
Okay, and then you put sheathing on it. And what they did is they essentially went up and they cut a bunch of lumber. I don't know if you guys have seen the pictures.
Mike showed.
Yeah, it's fucking cool. One guy goes in there with a chainsaw and cuts the damn thing out. And it was like 2 months after they did a similar dome it was very soon after they did a similar dome like on the East Coast, and they did that and it fell down. And what they realized was if you did at the time they couldn't do computer